Okay?
Okay.
Okay, fair enough. Okay, so what I'd like to do now is to get back to what we were talking about last week. Last class, we were talking about rankings, numerical rankings. Uh-oh, trouble. Hold on. Let me just finish this process. Yeah. Okay, hold on. No. Uh-oh. Okay, we may have some problems here. Um, okay. Okay, so last class we were talking about this idea of rankings, ranking functions that we're going to take as input, data, and we wanted to on a universe of n things, and we wanted to try to come up with either a score of the merit of these things. In the movie problem that you're going to be working on, there's this merit. What is the merit of the cast that you have for a movie? Okay. In chess, it was a merit of a chess player. Okay. In football rankings, trying to figure out how good football teams are, it's the merit of the teams. Okay. And we talked about, started talking about ranking methods. And I mentioned the ELO method based on pair comparisons. Any questions about that? We talked about ELO last time. That was a way you started out all things were equal based on the results of an incoming stream of comparisons, in this case, games between things. Okay, you give points to the winner, you take off points to the loser, but the amount of points you take off or give is a function of how surprising the win is. If you have a big difference between the things, you would expect that there is going to be, the fact that the better player won is not surprising and points shouldn't change hands, okay? On the other hand, if there's an upset, points should change hands. Any questions about that?
So Professor, how do we get the surprise part, the essay thing?
So the essay is the result of the match, okay? So you actually play the match or you do the comparison, right?
Right.
And once you have done the comparison, you know who won, lost, or drew, right?
Right.
So this is the outcome of the match. This is this is what we expected the outcome to be based on the score difference. And then we give points that are a function of the surprise level of the outcome versus the expectation, and our parameter measuring the swing. Okay, how sensitive should we be to what's the maximum number of points that should change hands?
So the surprise is SA minus mu A. Is
It's
is
the
it like the
actual
entire thing?
outcome minus the election.
Okay.
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 Right now in the election, okay, it is predicted on the website I follow that in the comparison between Trump and Biden, okay, it is when I saw a 78% chance Biden's going to win, right? Suppose they hold the election and Kanye West wins, okay? Do we have a high surprise value or a low surprise value? That is a high surprise value. Kanye's West stock should go up very, very, quite a bit after that. Okay.
Right. Right.
Whereas, it would not be as surprising if Biden won. And it would be, a little surprising, but not, a 22% chance if I did my math right, that Trump won. Okay. And that this would sort of reflect change if their ratings, okay, based on what the outcome of that was.
Right.
Okay, any questions?
So this is a rating of the algorithm, right?
This is a rating of entities. Again, let's go. Remember what we have. A and B are A and B are players. Okay, they are things that we want to rank. Okay, in the case of your casts, for example, maybe for every movie we want to come up with a ranking of the cast. Okay, a score associated with the cast. Now, I don't think that we don't get paired comparisons from that. But the input here is that we want to know, in response to a match between A and B, how does the outcome of that match, the outcome of that comparison, change our view of how good A and B are? Okay? And it's a function of how much it changes our opinion of how good A is. This is the old opinion, this is the new opinion. How much that changes is a function of what our surprise is in what the result of the match came out to be. Okay, so S sub A was the observed outcome, mu A was our expected outcome, and we were able to compute the the expected outcome was the probability that I should win plus minus the probability that I should lose. And this is sort of a win is a 1, a loss is a -1. Okay, and so the expected outcome is it should be 1 times the probability I win minus 1 times the probability I lose. If it was 50-50, I was playing someone just as good as me, my expected result would be that I end up in a tie. That would be 0. Okay? Any questions? And to get this probability, we use the logit function. The logit function was a function that had the nice properties that when there was no difference, if X, the argument, is the difference of the rankings of the two contestants, if there was no difference, it should be a 50-50 match. If my score is unbelievably higher than yours, then darn it, we expect I'm going to win. And if your score is unbelievably higher than me, then darn it, you expect me to lose. Okay? And the logit function, okay, which is given over here, has these properties. Any questions about ELO? So if you have data that's coming in by a stream of comparisons, as happens naturally in sports, okay, but happens often in other things that are not sports, okay, if you look out for it. And I'll show you an example maybe a little later on where you get paired data that is not just from sports, okay? Any questions? In fact, maybe I could take a look at it, another way to think about it. Anyway, let's talk about it later. Actually, let's look at another example just while we're just talking about it. Suppose, let's say that, you want to rank universities and you go and ask experts, okay? If they said, if you ask somebody, which school is better, Buffalo or Stony Brook? That is a paired comparison, right? The results of that should be something that if you are asking people for reputational information by giving them 2 things and saying which is better, well, that's exactly the kind of data that an ELO algorithm could use to come up with a score or a ranking. Any questions?
I do have a quick question, actually.
Yes.
It's a bit tangential, but when you say how the ELO takes into account the surprise of an outcome, it makes me think of information theory and entropy. Do you know if there's any kind of interpretation out there that puts it in terms of information gain as how the score goes up, I guess?
I haven't seen that, but you're right. Again, it's sort of it does have this. You're right that it has this information theoretic flavor that that again, surprise, it corresponds to information. Okay, so yes, so I can see where you're coming from. I don't have anything particularly interesting to say about it. Okay. Any other questions? Okay, let's look at a couple of other methods for coming up with rankings and scores of things. Okay, and often the data that we have to rank from, okay, it comes from, let's say, a voter where each voter ranks the candidates in some kind of an order. Okay, so suppose we had somebody where we wanted to figure out what the best universities were. Okay, and they said Stony Brook was the best, MIT was second, Illinois third, so on. What do we learn from this ranking? Well, we learned the voter was crazy, probably. Okay, but there is a common task where you are given a bunch of different voters, okay, a bunch of different orderings of the items, okay, and you want to merge them to get some kind of a consensus. Now, in principle, you can do this on any data set. Suppose you have a data set where you have a bunch of rows and columns, okay, and there are, n entities that you care about. And there's a feature 1, feature 2, feature 3. If the features have a property that they naturally correspond in an order from where, let's say we wanted to talk about wealth, well, a bigger number is better than a smaller number. And you could sort that by the feature value, and that gives you an ordering. Let's say we wanted to measure the amount of, heart disease you have. Maybe your cholesterol. Cholesterol is a bigger number is bad. So you'd want somebody with low cholesterol ahead of somebody with high cholesterol. Does everybody see that if you have n things, you have a matrix where you have n things and you have a bunch of features on them? You can interpret this, each column, as being a ranking. So long as you have an opinion as whether big values are better than little values. Okay? Any questions about that? So quite often we have a world where we would like to construct a ranking from a bunch of votes. Okay? So what is this picture here? This is kind of an example of this data a little bit. We have actually, although this is actually a transposed matrix from what I actually have, in this world we have 5 voters or features. That's another way to think about it. And this is going to be the ranking kind of for each voter from best to worst. If we have a situation like that, suppose in this case, actually, let me just make sure I actually hold. Right. Okay. Wait. Actually, hold on. Let me just make sure I've got this thing. No. Forget what I just said because my background's wrong. Actually, hold on. Let's interpret this data as, okay, the items are ordered that one means best, and 5 means worst, and there are 4 different voters, V1, V2, V3, V4, and there are 5 items here. Okay, the items are A, B, C, D, and E. Voter 1 thought A was best, C was second best, B was third best, D was fourth best, and E was fifth best. Does everybody get the interpretation of this matrix? Here we have the equivalent of 4 voters, and I'll call them, these are voters, or again, features. Okay? And we have ordered the items from best to worst. Is there a way that we can figure out a scoring or a ranking of what the merit of these items are? Well, there's a method called Borda's method that generally works by assigning a point total based on where you finish in the order. So suppose that you get 1 point for being first, 2 points for being second, 3 points for third, fourth, fifth, okay? A gets a score of 1, now you get 3, 4, 5. Does everybody see that? B gets a score of 3, 4, 5, 6, 7, 8. Okay? That basically, for each item, summing up what its ranks are, okay, gives us a score. If we sort the items based on these scores, we get a ranking. The consensus ranking is A, B, C, D, E, and there are associated scores with that. Okay? I don't think I did a great job explaining that, but do people get the idea of how this works? If we interpret our features as orderings of the items, okay, we can assign for each feature, each item gets a point, a certain contribution of points based on where it ranks from best to worst, and the total score gives us a way of ranking it. Any questions about that? Okay, any comments about that? This, by the way, is how, if you look at the top 20 football teams, at college football teams or basketball teams, this is basically how it works. They go and ask the, certain knowledgeable football people, like coaches and things like that. Who do you think was the number 1, 2, 3, 4, 20 top 20 teams? And then based on a method like this, they give a score, a consensus score, to identify what the type teams are. Things like this are used to rank universities based on academic programs. If they ask me, what do you think the order of the top 20 teams, schools are in computer science? Okay, I could give such a vote, and other people could do it, and then taking an aggregate from other people, you get a consensus. Any questions about that?
Yeah, the weight of the different voters, how do you compute that?
Okay, so now then the question is if there's schemes that you could tweak this thing. So the one thing you're saying is, what if we have different voters? Should we weigh different voters differently? Okay, if we know something about the voters, okay? So some of you may be thinking in terms of a machine learning technique called boosting, where if you're trying to train a classifier, you may figure out some voters are better than other voters, okay? But that's not really the case. If you do know, for example, that if you're rating computer science departments and you ask professors and you ask graduate students and you ask undergraduates, you might well decide, I'm going to let the professor's votes count for 3 times as much as a graduate student. And a graduate student counts 5 times more than an undergrad. Okay, you could imagine a world where you assign, each voter gets a multiplier, okay? And that way, voters you trust more, they get more contribution. That's one way you could tweak it. But the more interesting way to tweak it, at least for my purposes from now on, are what are the scores that you should give based on the rankings? Here, I'm giving I'm saying first place is worth 1 point, second place is worth 2 points, third place 3, 4, 5. Implicit in a score like that is that the difference between the number 1 item and the number 2 item should mean as much as the difference between the number 3 item and the number 4 item. And that only makes sense if you really have great confidence in your judgment of what the merit is, okay, in all positions, okay? And what I would argue is that most feature values and most knowledge, for some value of most, okay? We normally think of things as being in a normal distribution. Quality should be in a normal distribution, okay? If I am going to rate you guys at the end of the semester, okay, suppose I want to have an opinion of how good you guys are, okay? I would expect that your scores at the end will probably be normally distributed. In a normally distributed thing, you have a lot more of the items, okay? A lot more of the items are centered fairly tightly around the mean. Do you think when I rank the people in this class, do you think I'll have more confidence that the first item is better than the first student in my rankings or better than the second student in my rankings? Or do you think I will have more confidence that the 42nd student in my rankings is better than my 43rd student? Where do you think I will have a stronger opinion? Okay. Does anybody have an idea? Does everybody have an opinion about where there should be more confidence in your opinion on things? Okay. Not hearing anything.
I think it might depend on the scores.
Might
But-
depend upon the scores. Okay. Well, if things are normally distributed, let's say that X is our vision of our quantity of merit, be it your grade or something like that. One thing that's true is that because there is more, because there are more items close to the mean than there are outliers, the outliers tend to be further spaced apart by by value, rather than the differences of neighboring elements near the mean. Okay, again, I don't feel I'm saying this as clearly as I'd like to, so let's try it one more time. Okay, we should agree that that if we were using a feature that we were observing, it's not surprising if it's normally distributed. If it's normally distributed, okay, and there's a certain amount of error or uncertainty in the prediction, in the measurement, if there's a small amount of additive error, all these guys, okay, in the middle of this could very well change their ordering. I probably don't have, if you guys tell me at the end of the semester, I will probably have a strong opinion who is the best student in the class, okay, and who that the second best student is, and that the first student is better than the second student. If you ask me, the student who ranked 43rd in my class compared to student 42nd, am I going to have a strong opinion as to which one of these is better? Probably not. Their average scores are going to be very, very close to each other. A small grading change on something, okay, would end up causing them to flip. Does everybody see? If I gave one more point on an exam, maybe this guy would have ranked ahead of that guy, okay? So the point being, I think that when you, look at, come up with your rank ordering, if you're a voter and you want to come up with your ordering from best to worst, you often have more confidence about the things at the extremes than at the center, okay? I'm going to be sure I know who the best student in the class is, and I'm going to be darn sure I know who the worst student in the class is by the end of the semester, okay? So what does this mean? Again, how many people, do people understand the point I'm trying to make? I'm getting a little too much silence from people because, at this point. Okay? Any comments or questions?
So what I'm getting is because the first and the last would be towards the tail, and the tail is usually small and it's like towards the opposite ends. So you'll be able to make the difference clearly, but whatever is in the middle is kind of muddled up. You won't be able to make the difference very clearly.
I think that's generally true, okay? And I think that if you guys think about it, that's probably true. And if that's so, then if we are going to award votes based on position, we should probably do it not based on, not based on a uniform thing, but we should arrange our votes. So becoming first, okay, gets a substantially more votes than coming second. But the difference between coming the n over second and the n over second plus 1 should be a lot closer. Okay, and so you shouldn't be offering you should be giving more points to the higher, the n over second than the n over second plus 1. But it shouldn't be overwhelming. Okay. In general, if you drew your weights from a normal distribution, it would do what you kind of want it to do. Suppose I have n items, and I sample n weights, uniformly in a normal distribution. So if they were 100th, I would sample it at what was the cumulative probability up to 1 over 100, 2 over 100, 3 over 100, 99, 100 over 100. Okay, and that's what would you expect if you sampled from the normal distribution uniformly by probability? The values will be very, very close near the middle. See how thin these bars are? That's because the values are close near the middle. The area in each one of these buckets is supposed to be the same. Okay? That's what it means to sample by equal probability. If you use these scores, okay, instead of the numbers 1 through n as the weight of finishing in position I, okay, then you will give more weight to differences at the tails than at the middle. And that's what you kind of would like. Any questions about this?
Yeah, that makes sense. But if we were to ask people to vote, if something were objectively better, like an outlier that is objectively supposed to be coming first, wouldn't it always have better votes? And then that could be pushing it forward. Should we also have linear position weights?
Okay, so in this method, the data that we are given the ranking algorithm is everybody's ordering from best to worst, right? So when I'm going to vote when I'm voting in the election, I am going to pick a Biden or Trump, and I'm going to tell you which one was first and which one is second, in my opinion. That's what a vote is. I am not telling them, my God, I hate the guts of candidate I. Okay? So in this case, the data was just a linear ordering. What I'm talking about now is how do we interpret linear orderings when it comes to trying to form a consensus of scores? And Borda's method would say, okay, that differences among the first and second items probably should be more important than differences between the n over second and n over first item. Any questions about that? Any questions? Okay. Another way that I like to achieve rankings, by the way, it has to do with using directed graphs. Okay? One way to think about a paired comparison, like I beat you in a sports event, or given the preference of this candidate over the other, I prefer this one, is to interpret it, each vote as a directed graph, where if I am like, if I like A better than B, I should add an edge from A to B in the graph. Okay? Does everybody see that if I treat a comparison as an edge from the highest ranked to the better to the worst item, I will get a directed graph. Now, have you ever had a problem in an algorithms class where you wanted to come up with an ordering of the vertices in a directed graph? Does everybody remember topological sort? Who here remembers topological sort of a DAG? Okay. Well, if we found an ordering, in this case, where we could draw these things, all the edges, they give an edge from A to B, and an edge from B to C, and an edge from B to E, and an edge from E to F, and an F from D to E, okay, and an edge from B to D, and an edge from G to F. This ordering has the property that it respects every single one of those votes, right? A bunch of people voted and decided one item was better than the other. If we took this graph of comparisons, if this graph was a cyclic, meaning it was a DAG, then if we came up with an ordering where all the edges went from left to right, that ordering is an ordering by preference, by power, right? The items on the, this is basically going to give you a topological sort. It would give you an ordering of merit from best to worst that is consistent with all the votes. Okay? So if you study topological sorting, that's one of the good things about topological sorting. What is the bad thing about topological sorting? This kind of idea of topological sorting, if we want to find an order of merit, well, sometimes there's more than one topological sort, okay? And so these would be equivalent orders of merit for this particular directed acyclic graph. The bigger problem is that directed acyclic graphs are rare. If I'm having everybody make votes on do you like this school better than that school, there is going to be some joker who is going to disagree with everybody, okay? And if you add a vote that is contradictory, suddenly the graph that you get of votes contains a cycle. And if there is a directed cycle among the votes, then there is no longer a topological order. Does everybody kind of get that idea? If you took an algorithms class, topological sorting would give you a way to rank all the vertices from best to worst efficiently if the votes came out to be a DAG. But if the votes are not a DAG, okay, you've got inconsistencies, topological sort doesn't look like it helps you. Any questions? That said, okay, it's still a good idea to think about these general ranking graphs. What I claim is, if you give me a directed graph where an edge from I to J is a vote that I prefer, like I is better than J, what we'd really like to do is solve an algorithm problem where could I find what is the smallest number of votes to disregard so that you leave me with a directed acyclic graph, okay? If so, I would like the ordering that's most consistent with all the votes that you have, okay? That's a perfectly sound way to try to do a ranking, okay? Now, unfortunately, finding what the smallest number of edges to delete to leave a DAG turns out to be an NP-complete problem. But there are a lot of heuristics that are quite natural to try to identify what is the order of the vertices that causes the minimum number of violations, okay, or a small number of violations, okay, of ordering from left to right. And the order that minimizes this, if you come up with a heuristic for it, gives you a perfectly good way to deal with that. Any questions? I will confess, in past years, when I did peer grading of student projects, I had students compare projects and say, here is one report, here is another. Did you like this project better than that project? And based on those kind of comparisons that students could make pretty easily, is this paper better than that other paper? I got lots of votes about each project. And then I found what was the ordering that minimized the number of contradictions, okay, the number of votes that I'm disregarding, okay. That was how I actually assigned grades under peer, ranked the papers from best to worst when I was using peer grading, because this is a perfectly robust way of doing it. Any questions about that? Any questions about this kind of idea of using graph orderings, vertex orderings in directed graphs to achieve rankings? Anything? Okay, fair enough. Now, given that we've seen a bunch of different methods for coming up with rankings, okay, it might be perfectly reasonable for you to say, is there a best way to deal with it, a best ranking method? And there's an interesting, and you know, kind of one of these, you know, philosophically very important results that shows that there is actually, for any set of, any kind of an electoral system that you would like to design, there is no way to design a way to take rankings from people, vote orderings from people, and come up with a solution with an election procedure that will satisfy all of a bunch of desired properties. Okay? Again, let's imagine a world where, again, we have an election coming up. We can imagine a world where we have a bunch of voters, okay? And we can imagine that the voters have to rank all the candidates from best to worst. Actually, in the United States, in the presidential election, Maine has an election system like this. There might be multiple parties on the ballot. You can vote for, maybe you're a liberal person, maybe you want to vote for the Green Party to be first. And then if the Green Party doesn't win, you like the Democrats better than the Republicans. We're imagining a world where all the voters rank all the candidates from best to worst. We'd like to now interpret this data in a meaningful way. What kind of choices might we have? Okay. Well, we would like it to have the property that, basically, you know, in the way we tabulate the votes, we want to know that for every pair of candidates, whether candidate A did better than candidate B, or whether it was a tie. You got to tell me the ranking order at the end. We'd like it to be transitive, so that basically in my system, if I like A better than B, and I like B better than C, then that means that A is better than C. Okay? I would like it to be the case that if every voter voted for A would win over B. I would like it to be the case that our system is not a dictator. I mean, one way you could have an election is to have everybody vote. and then throw them out and just take Skena's rankings. That would be an effective way of doing it, but it would be a dictatorship. Does everybody see that? And we would like to know that if our voter system is good, whether the voters prefer A or to B should have nothing to do with any other candidates that are there. Okay? So Arrow's impossibilities theorem says that there is no way to design a way of tabulating votes such that all of these natural properties are simultaneously satisfied. And to give you an example, it's kind of a flavor of the kind of paradoxes you have here. Suppose we have 3 voters, okay, voting on what color they like best, okay? When we look at this data, okay, X likes color red best, Y likes color blue best, Z likes color green best. When we look at the data from all 3 of these candidates, from all 3 voters and on all 3 candidates, what do you think the outcome should be? You as a vote, someone who tabulates the votes, which color should win? Is it red, green, or blue?
It's a tie.
It's a tie. So you're telling me that you think that red and green are equal, okay, for example, by this. Does everybody, it looks to me like it should be a tie, right? But what happens if I say candidate blue drops out? Now what would the votes be? Well, voter X likes red to green. Voter Y likes red to green. Voter Z likes green to red. Now, if candidate blue drops out, who's better, red or green?
Red.
It looks like red is, right? And that's kind of not something we would like to have happen. We would not like to imagine a world where the candidates are all tied, but if one of them dropped out, suddenly there's a clear winner. Okay, so this is something that's kind of a paradox about designing electoral systems. To interpret it in terms of what we're doing in here, okay, it's a argument that there really isn't a best way to combine votes, okay. But on the other hand, if the kind of heuristics we do use in general, except, generally produce meaningful results, okay? Although there are these paradoxes and sometimes bad things can happen. Any questions about ranking or anything like that? Going once, twice. Okay. So what I'm going to tell you, I ran a little long, I guess, because we had a lot of questions at the beginning, which was good, and I like that. I was going to end today's class by going through the list of graduate projects. I know you now have a homework that is due in about 3 weeks. I want you to, I've also posted to the website a list of possible graduate projects. It would be good if before the beginning of next class, you guys took a look at them, just so that you're ready for, because I'm going to start next class by discussing how we're going to deal with the graduate projects, and it's probably good for you guys to look at that before we get going there. Any questions? Okay. If not, thanks for your attention, and I will see you guys soon. I'll see you guys on Tuesday. Okay? Thanks a lot.